We are now dealing with the entire universe. Okay, we're now on a universal scale. Now, once we get to this size, we have to make some simplifying assumptions. Okay, so these assumptions are what is known as the cosmological principle, and the assumptions we make is that the universe is homogeneous and isotropic. So the idea of homogeneous means that it has the same consistency or density throughout. The place that I've seen this before is on milk. There's homogenized and non-homogenized milk. The stuff that you usually get is homogenized. But it is possible to get non-homogenized milk. Non-homogenized means that it's going to separate. And as it separates, you get milk on the bottom and the cream floats out to the top, and you actually get these distinct layers. Homogenized milk has had a process happen so that the cream does not separate, so that any piece within the milk is all the same. This is what we think is happening in the universe, that overall, on the large scale, everything has basically the same density. Now, this absolutely does not work on the small scale. You do not have the same density as the Earth or the Sun or whatever. But this only has to work on a universal scale. We have to get up to a big enough size to see this working. And again, this appears to happen. Once we get to around 150 million light years across, then in a lump of space that big, we see roughly the same number of galaxies and voids in any region in the universe. So it does seem that the universe is homogeneous. The other piece is isotropic. Isotropic means that there is no preferred direction, that all directions are the same. And again, this only has to hold true on the large scale, and it does, or at least it appears to, that no matter what direction we look, we see the same sorts of scale for voids and clusters and that sort of thing. So all directions also appear to be equivalent. We can actually make an extension to the cosmological principle. So the cosmological principle itself states that it's the distribution of matter that is homogeneous and isotropic. But we can extend it and say that all physical law must also be the same everywhere, that the physics of how the universe works is also homogeneous and isotropic. Now, what this means is that the physics that we learn and figure out here on the Earth, we can then apply to anywhere in the universe. As we understand how gravity behaves here, we can apply that to everywhere. As we understand how light behaves here, we can apply that to everywhere. Here is our third lecture quiz question. What is the Hubble law? A, the mass of a galaxy's black hole is proportional to the galaxy's luminosity. B, we see more spiral galaxies in the past than we do today. Or C, the recessional velocity of a galaxy is proportional to its distance from us. Go ahead and think about it, and we'll discuss in just a bit. All right, what is Hubble's law? It has to do with distances and speeds. Specifically, it is C. The recessional velocity of a galaxy is proportional to its distance from us. In other words, the farther away the galaxy is, the faster it's moving away from us. So we've talked about Hubble's law previously, and if we just think about it quickly, it kind of makes it sound as though we are the center of the universe. So specifically, we see all galaxies moving away from us, right? All galaxies are redshifted. That's actually not entirely true. The Andromeda galaxy is blue shifted. The Andromeda galaxy, the closest large galaxy to us, is actually on a collision course. It's expected to collide with our galaxy in about 2.5 to 4 billion years. In other words, you don't have to worry about it, but if any of us are still alive then, it's going to be awesome. Anyway, so most galaxies are moving away from us. One way of interpreting that is that we are actually the center of the universe. Think about an explosion. When something explodes, you have all of the bits move away from some central location. Well, we see all things moving away from us, and therefore we have to be the center of the universe because we're the center of the explosion. How many times have we thought that we were the center of everything? And how many times have we been right? So maybe we should go ahead and assume that anytime it looks like we're the center of stuff, it's just that we don't understand what's actually going on. Okay, so no, we are not the center of everything. So we'll take Hubble's law, and we will then apply the cosmological principle. So remember, the cosmological principle states that our view cannot be unique, okay? That the universe is the same everywhere. So what is happening here must also be happening everywhere. So according to Hubble's law, we see most galaxies moving away from us. If we then move to some other far distant region of the universe, to some far distant galaxy, they must see the same thing. They must also see galaxies moving away from them. And then if we move to some other far distant galaxy, they must also see most galaxies moving away from them. In other words, all galaxies must be seeing most other galaxies moving away. So all galaxies have to be moving away from each other. Well, the only way that all galaxies can be moving away from each other is if the universe itself is expanding. I realize that probably didn't make a lot of sense, so let's use an analogy. In most astronomy textbooks that I've looked at that delve into this idea of the expansion of the universe, the analogy they use is a loaf of raisin bread. Personally, I don't know why you would take a perfectly good loaf of bread and then ruin it with raisins. So instead, I'm going to suggest that we have a loaf of cinnamon bread with chocolate chips in. I hope we can all agree chocolate chips are better than raisins. Okay, so we have our loaf of cinnamon bread and we've kneaded in the chocolate chips. We then set the loaf to rise. The entire loaf itself is going to expand. Then, as the whole loaf is expanding, the bread inside the dough is also expanding. And as that dough expands, it actually pushes the chocolate chips away from each other. Then, as we take a look at the position of these chocolate chips, every chocolate chip is then going to be pushed away from every other chocolate chip. This is what we believe is happening to the universe. It's not that the galaxies are flying away from each other, it's that the universe itself is growing like the loaf of bread, and as it does, it is pushing the galaxies away from each other. Alright, so let's take a look at what this means for an expanding universe. So in this case, we have galaxies that are separated by 100 megaparsecs. So from A to B is 100, from B to C is 100, from C to D is 100. Now we're going to pretend that we are on galaxy A looking out. So we see that from A to B is 100, from A to C is 200, and then A to D is 300. Okay, so we know how far away galaxies B, C, and D are away from us. B is 100, C is 200, and D is 300. Now this is one snapshot in time. We're then going to allow the universe itself to expand, and then we're going to measure again. Okay, so we jump forward to, I don't know, billions of years, and now from A to B is 150, from B to C is 150, and C to D is 150. But remember, we're on galaxy A. So from our point of view on galaxy A, galaxy B is now 150 megaparsecs away. Galaxy C is now 300 away, and galaxy D is now 450 away. Okay, so notice that all of these galaxies have moved away from us because of the expansion of space. But also notice how much they have moved. So galaxy B used to be 100 megaparsecs away. Now it's 150, meaning that it has moved 50 megaparsecs. Galaxy C used to be 200 megaparsecs away. Now it's 300 away, meaning it had to move 100 megaparsecs. And galaxy D used to be 300 away. Now it's 450 away, meaning that it had to move 150. Now, all of this motion took the same amount of time, that same 200 billion years that we had. Okay, so in 200 billion years, galaxy B moved 50. In 2 billion years, galaxy C moved 100. And in 2 billion years, galaxy D moved 150. In other words, galaxy B moved, but it moved the slowest. Galaxy C moved faster than B, and Galaxy D moved the fastest. So the farther away the galaxy is, the faster it had to move. This is exactly Hubble's law. An expanding universe, Hubble's law is a consequence of the expansion of space itself. Now, I realize we used it to help us figure out that space itself had to be expanding, but the Hubble's law is actually a consequence of the expansion of the universe. All right, here is our fourth lecture quiz question. Which color of light has the longest wavelength? A blue, B green, C yellow, D orange, or E red? Go ahead and think about it, and we'll discuss in just a bit. All right, which color has the longest wavelength? The answer is E, red light. Red light has the longest wavelength. And because I mean like this, here is a fifth lecture quiz question. Which color of light has the least energy? A blue, B green, C yellow, D orange, or E red? Go ahead and think about it, and we'll discuss in just a bit. All right, so what color has the least energy? It is also E, red light. Red light has the longest wavelengths and least amount of energy. Well, previously, when we talked about how it is that Hubble's law came to be, where we realized that galaxies were moving away from us, and the farther away they were, the faster they were moving, we presented this red shift of galaxies that we were measuring as if it were a Doppler shift. And to be fair, this is what Hubble actually interpreted at first. However, that's not what's actually going on. The galaxies are not redshifted because of their motion. The light from the galaxies has been redshifted because of the expansion of space. I realize that sounds really weird. Okay, so what happened is that the light was emitted from the galaxy. Then, as that light has been traveling through the universe, space itself is expanding. And as space itself is expanding, it stretches out those wavelengths. So it was emitted at some wavelength, then it has been stretched out over time, so that now it is a much longer wavelength than it used to be. This is what is known as cosmological redshift. So we've talked about Doppler redshift, we've talked about interstellar reddening, we've talked about gravitational redshift, and now we're adding cosmological redshift. There's a lot of redshift going on in the universe. So some things that I want to bring out about this expansion of the universe. Okay, so sometimes when people hear it for the first time, they interpret it as galaxies are simply moving away from each other. Okay, and this is also kind of what we thought originally. Okay, so the galaxies used to be close, and now they're moving apart. This is not what is happening. What is actually happening is that the galaxies used to be close, and then space itself is expanding, and as space itself is expanding, it's drawing the galaxies away from each other. Okay, so it's not just that the galaxies are moving, it's that space is pushing them apart as space grows. Another one that I've heard is that as the universe is expanding, so must everything inside the universe. Okay, so in other words, atoms today are larger than atoms used to be in the past. The Earth today is larger than the Earth used to be in the past. Okay, again, this is not what is happening. Okay, so what holds an atom together? You've got the positive nucleus and the negative electrons going around. Okay, that is an electromagnetic attraction, positive attracted to negative. That attraction is stronger than the expansion of space. Space is expanding, but the attraction between the positive and negative holds the atom together, and space expands around it. Okay, the same thing's happening to the Earth. Gravity is holding the Earth together, and that gravitational pull is stronger than the expansion of space. Okay, so space expands, but the Earth is still held together. Okay, same thing's happening with the solar system and our Milky Way galaxy. Gravity is holding all of this together against the expansion of space. Now, this works all the way up to the scale of a galaxy cluster. A galaxy cluster has enough mass and enough gravity to be held together against the expansion of space. Space is still expanding, but gravity's holding these things together. This doesn't work on the scale of a supercluster. There's not enough gravity holding the clusters together in a supercluster against the expansion of space. In other words, galaxy clusters in a supercluster are spreading away from each other because of the expansion of space.